let's continue. So you have access to the code. So in this code, we're going to first go over two decision trees, then bagging, then random forest. So then I will explain boosting in the end. So here I'm just loading the data sets from scikit-learn. This is a data set on children car seats. So it's about sales of children car seat, and then we have features on price of our competitor in that city, the income level, average income of people in that city, the budget of advertising we had for that city, population of that city, the price of children car seat that we sell in that city, shelf lock, whether it was good, bad, medium, I guess median age of people in that city, level of education of people in that city. But I mean, I say city, but it's like a location on that branch, whether that branch was in an urban area or not, whether it was US or not. And then there are no null values in this data set. So what we're going to do is use these as predictors. I guess it's all of these as predictors for a classification task. So we created a new column called high, very different, very strange name. So it means whether the sales in that branch was more than 8,000 units. So, and then we're going to fit a decision tree, a decision classifier that looks at these features and creates a flowchart that, based on asking a couple of questions, we can predict whether sales would be high for a branch or not. So here I'm considering, so there are 400 data points. I'm considering 300 of them as training data. So I'm doing a two-way split between training and validation. For building the decision tree, I'm using maximum depth of 4 and minimum sample leaf of 4, which means that if there's a region with 4 samples, I'm not going to split that anymore. So for fitting the decision tree classifier, I'm using the GNI impurity as the objective function and these two stopping criteria. So I'm fitting to the data and then measuring the accuracy on the training data. The accuracy is this. So the only thing that matters in here is that we don't want this accuracy to be 100%. If it is 100%, it means we are overfitting to the training data. So now we can also visualize the decision tree. So you are business students. You know this better than me. For sales, what is the most relevant predictor of sales in general? This is not about this course. Isn't it price? You know, if we just sell something, 99% off, we're going to sell a lot. That's what the algorithm also understands. It says the first question I'm going to ask is whether, sorry, my question was a bit spontaneous. So the first question that the algorithm asks is whether the price at which we are, selling these car seats is less than 92 or not. If the answer is yes, then we move to this region where we have only 45 samples. So, yeah, let me zoom in a bit. So we move to this region where we have 45 samples. And you can see that GNI impurity becomes 0.32. At the beginning, GNI impurity, it's just too dark. So GNI impurity here, it's 0.47. And I told you that for binary classification, 0.5 is the largest value of GNI impurity. So at the beginning, our classifier is totally clueless. It cannot make a distinction. Then for this region, GNI impurity is 0.32, which means that this region is a bit more homogeneous. And also when the answer to this is no, then we move to this direction and we end up in this region where again the GNI impurity has reduced a bit. So the way to read this is, the first line is the question we're asking at that branch, at that node. The second is telling us the objective function, which decreases over time. The third one says how many data points belong to that region. So at the beginning, it's all the data points, 300 data points. Then after this split, 45 of them end up here, 255 of them end up here. Then value shows the distribution of the two classes between those samples. So from the 300 samples that we had, I guess 181 of them belong to class 0, which means sales was not high. And then 119 of them belong to class 1, which means sales was high, was higher than 8,000. So you can see that when price is less than this, we're going to, so when the answer to this is a yes, then we end up in this region. And in this region, out of 45 branch, for 36 branch, for 36 of these branches, sales was high because price was low, right? And then in cases where price was high, you can see that more often than not, sales was low, right? So it just asks a couple of these questions. The next question is about shelf lock, then about population of city, about income, advertising, and eventually we get these regions. And in these regions, you can see that for many of them, GNI impurity is like really small. Here it's 0, because this is a pure region of 4 samples. All 4 samples were cases where sales was low, was not high. This one, again, GNI impurity is 0. 46 samples, in all of them sales was low. This is, again, a region with GNI impurity of 0. In all of them, sales was high. So then this kind of flowchart is our model. If you want to make a prediction, you can tell me what would be the predicted number of sales if we spend this much on advertising, if we price our product at this value, in a city where income level is this, where median age of population is that. Then based on that those pieces of information, I'm going to follow this flowchart and end up in one of these boxes. Then based on these boxes, based on the more likely outcome, I will give you a prediction. So if I end up in this box, where there has been 9 samples, 8 of them with low sale, my prediction is that sale would be low, right? Then you're going to change your numbers and say, all right, what if I spend, 5,000 more on the advertising, right? Then I, again, follow the flow chart, and then I can, again, give you a prediction. So you can see that it's very interpretable, but the predictions are not that good. So here I'm creating the confusion matrices. So for the training set, the confusion matrix looks like this. For the validation set, the confusion matrix looks like this. The accuracy on training set is 83%. On the validation set is 66%. So very disappointing. But as I said, decision trees are not, famous for good predictions. Actually, their predictions are usually bad. So that's why we need advanced tree-based models, so we can try more advanced models, like a random forest or bag tree, to see if we can improve this. Also, we went with some arbitrary numbers for depth of the tree and minimum number of samples per leaf. Possibly, if we change those hyperparameters, the performance changes. But more importantly, decision trees are not that capable, so we don't really invest that much time in improving them. Instead, we use like random forest. Yeah. So decision trees are models that have been around for, I don't know, maybe more than half a century. Um, so their advantage is that they are meant to kind of mimic how people make decisions, apparently. So if you go to a restaurant and you're making the decision whether you should wait for a table or not, apparently that depends on whether, well, first of all, whether it's full or not, how hungry you are, if you have other alternatives, right? So that's something that you can just draw with a flow chart, right? And then in situations where you're unsure, you ask the waitress how long would be the wait. Again, based on that information, you can make better decisions. So in that sense, it's kind of intuitive, but as an idea for machine learning, it's not that good. But the thing is, it's kind of the building block of random forests and boosted trees and bagged trees. Yeah. Which one? We are not deciding on this. The algorithm is creating boxes which contain these many data points in each of them. So like this thing is some region 1, this thing is some region 2, this is like a region 3. Yeah. Yeah. So let me explain. So there are 300 data points at the beginning. Then we make one split, which is these two lines. It's result of one question. And those 300 data points become these 45 data points and these 255 data points. So these two numbers add up to 300. Also 9 plus 172 add up to 181. Yeah. So what this means is that in each kind of level of this tree, each sample is exactly in one of the boxes. So at the very end, each sample belongs to one of these regions, these terminal nodes. So the next example, any questions? The next example is on a regression tree. So for this one, we're using Boston housing prices. So it's a database on, prices of, I guess, property in Boston in, 1960s or something. And one relevant variable is LSTAT, which is fraction of poor people in that neighborhood. So we're fitting a decision tree based on max depth of 3. And then we can here visualize the decision tree, the regression tree, and you can see that the first question it asks is about LSTAT, right? So what this means is that for Boston, we know that the most relevant predictor was LSTAT, was number of poor people in that neighborhood. If in a neighborhood, number of poor people is less than 7.8%, the price of houses is 32 something. If the number of poor people is more than 7%, the price of houses is 18,000 or 18 something. It's based on, 1960s, I guess. Buy a house for $18,000, right? So then you can see that then there are splits based on, number of, I guess, RM is like a different variable, right? But then based on these numbers, we end up with these boxes. And for each box, we have value. Value is the prediction. What this means is that this regression tree only has one of these predictions. Whatever house you ask about, the prediction is either 50 or 28.008, one of these discrete values. And that's one reason why they are not as good as like linear regression. So we can also look at MSE, mean squared error, on the validation set. MSE is 26, right? And yeah, so that's That's a regression tree. Now we can use more advanced models like bagging. So the thing is, as random forests are just a more advanced version of bagging, actually, I guess in scikit-learn, there is no specific function for bagging. If we want a model of bag trees, we need to use random forest, but then provide all the features to it. And that would become bagging. So if we use a bagged model, and we look at the MSE on the validation set, now it's 17.14. So my question for you is, which of these models is better? The regression tree with the error of 26 or the bag tree with error of 17? Bag tree is better. So then, so next thing we can try is an actual random forest where we provide 3 features to the tree growing algorithm, right? So we had, I guess, like 13 or 14 predictors. So the square root of 13 is almost 3. So let's use 3. So this is like a random forest with m being equal to 3. So now the mean squared error for this model is 15.3. So my question for you, is random forest a better choice or bag tree? Random forest. And this also kind of matches with kind of the history of this idea. So bag trees, if I'm not mistaken, is an idea from 1980s, and random forest, I guess, from 2000s or 1990s, and gradient boosting or boosted trees from 2000. So the newer kind of the more contemporary ideas are kind of expected to be a bit better. So, yeah. All right, so then also as a side product of these models, we also get something that is called variable importance plot. So as we use these features to make splits, and then based on the split, some objective function decreases, we can look at how much reduction in total we had for each of the predictors. So the predictor that gave us the highest reductions is the most important predictor. And we can kind of plot that. That's just a byproduct of these models. And you can see that, for example, for this model, it says for Boston data, LStat is the most important variable. Next important variable is RM. So this is comparable to how in linear regression, LStat may get a large coefficient, the effect sizes, right? So the